This is lecture 7 on principles of mass transfer. So, so we are looking at mass transfer principles. Okay? Mass transfer principles. In that, we are actually seeing the general equation and the fixed law equation, molecular diffusivity and convective diffusion. So this molecular diffusion in liquids, first of all, if I just imagine gases, in gases or diffusion coefficient. Okay, we have seen diffusion coefficient earlier in the fixed law equation. Diffusion coefficient in a gas will be of the order of 10 to the power of 5 times greater than that of diffusion coefficient in the liquid. The flux in the gas is not that much greater, but flux is only 100 times faster, but diffusion coefficient is what is very important to us. Because in the liquids, the what do you call molecules will be intact, right? And wherein we see this molecular diffusion in liquids, many industrial processes, that is liquid extraction, we say, or solvent extraction, or gas absorption, and also distillation. Okay, this is very important to us. So some of the in the human body, diffusion in liquids in nature, oxygenation of rivers or diffusion of salts in blood. Yeah, our blood flows, there is a diffusion of salts into the blood. Now, generally, the equation is written in terms of C, concentrations. And of course, when we say in terms of liquids, we can also mention X. In gases, we mention Y generally, but here we can say generally the equations are taken up with these terms. So, what is the joules? What is the fixed law as per the equation here? If you see, JAZ, it is just rewritten. Solvent separations are done. Sorry, variable separations are done. What is done actually? JAZ is equal to minus DAB TCA by DZ, right? So this is what we write. But what we are saying is that we want to actually come to a relation. So we take a boundaries from one point to another point. So then we are trying to write in this way. So that means you can see Z1 and Z2, CA1 and CA2. That means from one point to another point, what is the concentration change? So ultimately, we can write this molecular diffusion as DAB into CA1 minus CA2 by Z2 minus Z1. In the similarly, if you club those two, this is convective and this is molecular level diffusion. So this Na we will be using. So what is this? What are the two situations? What are the two situations in equations for diffusion in liquids? Number one is equimolar diffusion. That means again the same thing. Na is equal to minus NAB, counter diffusion. See, equimolar counter diffusion. So the same thing we'll be using in the equations. Another one is Na will be there, but Nb will be 0. See, that means non-diffusing B. One is non-diffusing, another is. So in the two cases, equimolar counter diffusion, we actually utilize this equation, and this is the equation we writing. See, you can see this is Na, and when I say counter diffusion, that means Na is equal to minus NB. So this total term will vanish, and then we'll left with upon integration and separation and everything. We will be left with this type of equations. That is nothing but Na is equal to DAB CA1 minus CA2 divided by Z2 minus Z1. If I write this CA1 and CA2 in terms of, what is CA1? So CA1 by total concentration, average concentration is equal to XA1. CA2 by average concentration is equal to XA2, right? So I convert CA1 in terms of XA1. That means C average into XA1 and CA2 as C average into XA2. So we can do this like this. Whereas Na is the flux of A in kg mole A per second meter square. DAB is the diffusivity. Ca1 is the concentration of A at 0.1, and Xa2 or Xa1 mole fraction of A at 0.1, and C average is defined as, so C average is this. Okay, C average is given by this as if C1 plus C2 by 2. So that is, what is C1? rho 1 by molecular weight plus rho 2 by molecular weight whole divided by 2. So this is the average weight. And again, M1 is again average molecular weight of the solution at 0.1. Rho 1 is the average density at 0.1. Similarly, next one is diffusion of non-diffusing B. That means Na will be there, but Nb is 0. So how do we write this? The same equation again, equation this. With that equation, we come to this particular equation. Na is equal to DAB CA average, Z2 minus Z1 to XBM, X7 minus XA2. This is well known. There is a suppose say we want there is something called A plus B, and A is propionic acid. Propionic acid, B is water, and we want to separate this mixture. We add with toluene. We add toluene as a solvent to this. Only propionic acid diffuse to the water phase to the boundary and then to the toluene phase. So there are two phases here. So it is one is water phase, another is toluene phase. So propionic acid only will diffuse through the water phase and through the toluene phase and enters the toluene. So the toluene water interface is a barrier. Okay, that means the toluene will not diffuse back into the propionic acid. That means NB is 0. Okay, that means if I say B is much water, water is not diffusing. Okay, so the most important case of diffusion in liquids is that where A is diffusing and solvent B is stagnant. Example, dilute solution of propionic acid in water. So here only propionic acid diffuses, water does not diffuse into the toluene. I am correcting myself. Previously I said toluene is the B. No, the water is B. So in that case, so this all will come into picture, and we write C average, all these terms. We change all these terms. Ultimately, we come to this particular equation. But here, if you remember, XA1 plus XA2, sorry, XA1 plus XB1 at 0.1, at 0.1 should be equal to 1. XA2 plus XB2 at 0.2 should be equal to 1. So for dilute solutions, XBM is close to 1. So this term vanishes. So for dilute solutions, you write this is simplified and written like this: Na is equal to DAB C average. That means C is then dilute solution is what? There is no average. C will be constant. So this C average can be taken inside. So C into XA1, C into XA2, that will become CA1 and CA2. So this is the ultimate equation. We'll go into the next session. This is the molecular diffusion in liquids.